All right, so I did assign tutorial problems using standard enthalpies of formation reactions, So I didn't really do too many examples of this, but if you do have questions regarding any of the homeworks or the calculations, let me know. Basically what we want is we want to have like a reliable amount of energy that we're going to get. And so the amount of heat, if we look at the heats of combustion, well, heat's not a state function normally. And so the amount of heat we get isn't always the same. It depends on the path. And so what we want to do is we want to have something that's reliable. That is, in this case, we want to always get the same amount of heat. And so one way to always get the same amount of heat is to do it in a bomb. We'd get QV, but that's not very useful for us because we don't burn fuels like this in a bomb. And so what would be a much more useful form of heat would be QP, but we have to restrict QP. QP means constant pressure, so not only do we use constant pressure, but we have to restrict it to what? Yeah, pressure volume work only. And if we restrict it to that, the natural order chemical reaction, then heat becomes a state function. So for example, if we burn a gram of municipal waste, I don't know how accurate this is. If you burn a gram of municipal waste, you should be able to get 12.7 kilojoules. Although I wouldn't want to do a calorimetry experiment with that. Actually, my friend he just graduated with his bachelor's degree in chemistry, and he went to go apply at Hyperion to get a job there. And they asked him, is municipal waste a reducer or an oxidizer or neither? And you know what he picked? He picked neither. But that's wrong because municipal waste can be used as a fuel. And so, anyway, he didn't get the job. But he came up to me and talked to me. What's that? What's sewage? Sewage, right. Sewage. I don't know, in some dystopian, a movie I might have seen it used as a fuel or something. Or maybe a food. Going on here, if you look at it per gram, which one do you think is giving the most energy? Here, natural gas. And so when we see this is what we call the net energy from here after you, subtract out the work. Or sometimes you have to add in the work, or maybe there's no work. And so this is the net. And so this is very useful because let's say we're given the gross. Let's say you wanted to go buy something, and this has happened to me. The object is $10, but it depends on what city you buy it in. If I buy it in Gardena, I got to expect to pay a little more than if I buy it in Torrance because the tax in Gardena is over 10%, and I think the tax in Torrance is less than 10%. And so you are always thinking, well, how much is it going to cost? I don't want to know, it's $10. I want to know how much I have to pay out of pocket. And so this is why we like delta H. We like the enthalpy. Enthalpy is going to be much more useful for us because this is going to tell us, after tax, or maybe there's no tax, or maybe there's a bonus, this is the amount of energy I'm going to get. Now, another odd thing is this is heat. This is heat of the reaction, but do we always burn methane for heat? Yeah, in laboratory we do. We burn methane often for heat. We want to heat up a test tube. We want to heat up a beaker of water. And so often we do that, but not always, because we also want to do work. So if I do this much heat out of this natural gas, 49.5 kilojoules per gram, how much work can I get out of that? Well, we already said we already compensated for the work because that's PV work, right? But that's not actually the case. This is what I call the net usable energy. And so what I mean by the net usable energy is that we don't have to convert the chemical potential energy. The chemical potential energy comes from methane burning, and that's going to produce 49.5 kilojoules. Now that 49.5 kilojoules per gram can go all to heat or we can convert some of that change into other forms of work. And so the worst thing you could do is to convert it all to heat and then try to convert heat into work. Converting heat into work is very difficult, but that's not what we're doing here, because this is, if you used all that energy to make heat, this is how much heat you would get. But if we convert that chemical potential energy, which is like the battery, into work, then we can get a lot more work out of that. Although we can't convert it 100% into work. We wouldn't be able to convert all this into 100% work because of things like friction and other types of things which would lead to heat losses, energy loss as heat. And so natural gas, I like natural gas because it burns cleanly. You know, sometimes if I'm driving behind a bus, I much prefer to follow a CNG bus than a diesel bus. You know, diesel bus is spitting out all these fumes and NOx and everything. It's very irritating on the eyes and the lungs. But a CNG bus is quite nice, and what they're trying to do in a CNG bus is convert as much of this as possible into work. And so they're just burning this in their engine and converting it into mechanical work. So this is very good. And so what are they saying here? They're looking at environmental impact or so. But we can see that natural gas natural gas burns very clean. There are people who want to convert, like some people live where there's only propane, or if they have a boat or something, or I've been reading about people trying to convert stoves on boats into natural gas from propane, because propane doesn't burn as clean. You know, if you have a propane barbecue versus a natural gas barbecue, sometimes there's a little bit of propane residue on the food. You can taste it. You know, it depends on how much residue there is. But natural gas is excellent. Hydrogen is good too, but hydrogen, you know, there are issues with that. But anyway, these are the fossil fuels here, or fuels. I shouldn't say fossil fuels. Not all these are fossil fuels. Wood, municipal waste is not fossil fuel. But natural gas is. Isooctane component of gasoline, coal. No, coal can burn very clean. All these can burn very clean. It's just natural gas, you don't need a scrubber, but for coal you would need a scrubber, because there's sulfur in coal. When you burn sulfur, it forms sulfur oxides, which leads to acid rain. But acid rain, have you heard much about acid rain? People aren't complaining about acid rain. People were complaining about acid rain a lot in like the 1980s because it was eating away statues. But nowadays, nobody complains, because why? They have scrubbers to clean the exhaust. So the exhaust coming from coal plants is a lot cleaner than it used to be. Most of the electricity in California comes from burning natural gas. But this is a chart showing energy consumption by energy source. But a lot of people are worried about this. You know, when you burn fossil fuels, you create CO2, you know, if you have good efficient combustion. And CO2 is a greenhouse gas. And what greenhouse gases do is, let's say we have light coming in here. This curvy line here is supposed to represent a wave of light. So light comes in here, gets absorbed, and this doesn't, whatever absorbs it doesn't stay excited, what they say, excited. Eventually it will drop to the ground state and emit radiation. And oftentimes this radiation that's emitted is just infrared. You can feel this on rocks or brick walls or whatever. During the daylight, the brick wall or rocks absorbs light from the sun, and at night you can feel the radiation, at least initially. You can feel the warmth coming off the wall or the stone. But what happens is this should escape out back into space, but it doesn't, because it gets trapped in the atmosphere. What happens is infrared radiation like this gets absorbed by molecules, And what infrared does to molecules is it causes them to vibrate. And so CO2 vibrates, absorbing the infrared radiation, and if it vibrates, what happens to the temperature? Temperature goes up. And this is called the greenhouse effect. And so CO2, people are worried about CO2 emission. There's lots of talk about trying to capture the CO2 out of the atmosphere to reduce the CO2 levels in the atmosphere. Here's some data presented in the book. You know, here they're showing the CO2 levels rising from 320 up to over 380 between 1960 and 2010. So the CO2 levels are going up. And then they're looking at the average global temperatures. This is more CO2 emissions data here. And they're trying to correlate this with global warming, essentially. And so the data, you know, we could look at the data and it looks like there's a pretty good correlation there, but there are people who don't agree with the current analysis. So we have the data. And so in science, we try to keep these two things separate. The raw data is what we call factual observations. But your analysis of the raw data we call analysis or discussion. And so in papers, we have the results, and then we have the discussion. So there are people who look at the results like this, and then the global average temperature, and might come up with a different conclusion than others, which is fine. This is how science is supposed to work. How science is supposed to work is that, you know, the raw data doesn't change because those are factual observations. So, for example, when I say, when I looked at some people's papers and they said, okay, we got the barium sulfate precipitate, but you don't say barium sulfate precipitate in the results section. You could say barium sulfate precipitate in the discussion section. In the results section, you should say white precipitate because white precipitate cannot be refuted. And it is a white precipitate, that's just fact, it's a white precipitate. But if you're claiming it's barium sulfate, then you have to have sufficient arguments to convince somebody that it is indeed pure barium sulfate. What are your arguments for convincing somebody it's pure barium sulfate? And so this comes down to this, you know, people will take that raw data and come up with different conclusions. And then you get these, you know, opposing sides, opposing opinions. And you might have heard about this. I've been hearing a lot about this. I've been hearing about climate deniers, you know, people who don't believe in the science. But, you know, I don't really like that myself because, you know, I would, rather than trying to censor these people, and there are even scientists that are trying to censor the climate deniers. Rather than trying to censor them, they should take their analysis and explain what's wrong with their analysis. That would be much more useful, I think. But anyway, what we do here is we take a look at the data and then just analyze it and come up with models. So people have come up with different models about, you know, how hot it's going to get. For example, some models say, you know, the world is going to come to an end, you know, within a certain time period. But, you know, how many variables can you put into such an equation? And so it depends on how reliable such models are, and such models are very difficult to do. And so we need the data. Okay, this brings up another point. The other point is natural gas burns cleanly, and except for the CO2. Otherwise, it's quite a good fuel. But there are problems with natural gas. Natural gas itself is a greenhouse gas. So cows end up emitting a lot of natural gas emission. And so there is a proposal. I mean, it depends on what the models are showing. Are the models showing that the emissions from the cows being a significant contributor to global warming, or not such a significant? If it's a significant contributor, is it justified to eliminate all the cows? Yes? Yeah, some people will say yes, for sure. A lot of people will say that, and they'll say just eat the synthetic meat, which people are doing, if you want protein. And so these are all these questions, but you know what some chemists are doing is they're trying to add additives into their food so that they don't produce as much methane. And so hopefully they don't have to eliminate all the cows, they'll just change their diet, and that might solve it. But we'll see. You know, that's UC Davis, I think, some work is going on there. Another thing is not only natural gas, but there are other molecules like water. You know, water vapor is an excellent greenhouse gas that absorbs energy. Interestingly, it's kind of weird to think about, but nitrogen and oxygen are not. You know, you have diatomic nitrogen, the vibrations there don't trap in the infrared.
Is a road thermodynamic closed or open system? It's like
the what?
Is a road like a thermodynamically open or closed?
The world?
Yeah.
The world is not a closed system. Things can leak out, but it's hard for certain things to leak out because of gravity. And so things can leak out, but it's difficult for them. But it's not completely closed, because in a closed system, matter and energy cannot be exchanged. And so if it were completely closed, then we would get no energy from the sun, and then we would die off.
Is there like a separate term for it then? Or?
It's, you know, some things, in some respects it's closed, in other respects it's open. You know. For the very, very light elements, it's open. So we don't have very much hydrogen in the atmosphere, and the helium is very, very rare too. The hydrogen and helium can escape Earth's gravitational pull. But that's an interesting question. You know, it's hard to model something that big. So when you see models, I'm always very skeptical of the large models, because usually there's large errors associated with these. Large models means there's a lot of variables in there. It could be a very small system, like a person, a human, you know. If they could model a human, then, you know, and people are trying to do this. People are trying to predict how long your life is going to be and what diseases you're going to be hit with and this kind of stuff and that kind of stuff. If you can model that, then, yeah, then maybe you could live your life, you know, to the fullest. If you know when you're going to pass, then. You know, you have people. I remember this here at this chemistry department. We've had 2 people retire from the chemistry department, and they're so excited because now they're going to do this. They're going to go travel there and travel here, and then a couple of years later, I hear, you know, there's a memorial announcement, and I thought, wow, you know, if they had known, maybe they would have done things differently. But how easy is it to model? You know, and then there are people who are claiming they can model such stuff and then predict exactly how this drug or that drug is going to impact. It's just like, how can you do that? The models are so complex. They're
like
going to be subject to errors. What's that?
Sounds like I missed something important.
No, nothing important. Nothing important, but you hear people who claim to know, you know, and then you gotta be very skeptical. I mean, that's just the scientific method. The scientific method is you gotta be very skeptical about anybody who claims to know, you know what.
So life insurance is a load of.
Well, apparently these models are very strong that the insurance companies can use it and actually make money. Yeah. So I mean, maybe I would like to get kind of analysis sometime, maybe. Or maybe you don't want to know. Yeah. So it's not just CO2 that can trap water vapor, methane. Those are greenhouse gases. Oxygen, nitrogen are not greenhouse gases. Those are fine. Those don't trap any heat in, oddly enough. So we're just talking about fuels. So we have other energy sources that, these are all combustion. So coal, gasification of coal. With coal you can make methane. From coal you can make hydrogen. There's different things you can do. Methanol, ethanol. Methanol and ethanol, these are not fossil fuels. Methanol you can get from corn, or not corn. Corn you get ethanol. Methanol you can get from fermenting wood. You can also get it from coal.
Is this on the next exam?
No, this is not on the exam. This is just general interest. Biofuels. Biodiesel was something that people were really looking into. Biodiesel, because you could use vegetable oil from restaurants and then use that for your car. But have you ever followed a biodiesel car?
Yes.
It's just like a crop duster. There's just so much smoke coming out of the exhaust. It's awful.
The worst is being behind one of those big buses with like the 5-liter engines.
Oh yeah,
That's
the big
terrible.
buses. I hate
And
that.
it's hot too.
Yeah, and then you're breathing in NOx and carcinogens and whatever else it's spitting out. Well, hydrogen could be good as well, but the problem is how do you get the hydrogen? You have to make the hydrogen, and how do you make the hydrogen? Well, it's not so easy, and it's very expensive. And so, I told you I test drove the Toyota Mirai, but you know Toyota's being sued. Did you hear that?
From the hydrogen cars?
From the people who bought the hydrogen cars. There's a class action lawsuit against Toyota because they.
Can they not refuel them?
They gave them, every car came with, they tried to make a deal. They came with like a gas card, but for hydrogen, where they paid, yeah, you heard about that?
Yeah, they were offering like 3 years worth of free
3 years
fuel,
worth.
which is good because apparently the price of hydrogen has skyrocketed. And so that was one of the complaints. The other complaint is there's supposed to be a lot more fueling stations, but none were built since they bought the cars. So there's only like 2 of them around here, I think. 1/90th. The other thing is, how do you make hydrogen?
The blue one.
And so have you heard about the hydrogen color spectrum? So hydrogen's labeled from green to pink. And it's not because there's actually green hydrogen. It's just how they make it. And so it's like our electricity. We pay for green electricity, right? But is all our electricity green? No. Green electricity means it's made by renewable resources like hydroelectric, wind, solar. But there's not enough capacity. So what we do is we end up paying a penalty for natural gas. They just burn natural gas to generate the electricity. Eventually it may become green completely. But anyway, we go back to this. Green hydrogen is hydrogen that's made from renewable energy sources. And so in order to make green hydrogen, you need to generate electricity. In order to generate electricity, they restrict it to solar, wind, hydroelectric. To generate the electricity, to generate the hydrogen, and then they call it green hydrogen. There's not enough green hydrogen. And so there are other sources of hydrogen. There's blue hydrogen. Blue hydrogen's produced from natural gas. It's natural gas and steam to make hydrogen, and like carbon monoxide or carbon dioxide here. So that's blue.
What is the octane rating against on fuel?
I'm sorry?
What is
Octane.
octane rating on fuel? Like how
Octane, when you get gasoline, you don't want it to burn too fast and you don't want it to burn too slow. It just has to burn at the right speed. Like too fast will cause an explosion, and explosions aren't good in your car engine because they causes detonation and it breaks things inside the car engine. And so so the octane rating is kind of based on how fast it burns or how slow it burns, and they use octane as the standard for that. Gasoline's a mixture, and so normally the higher the octane, the less detonation you get.
So if I have like a really poor 97 Civic and I put like premium fuel in it, it's gonna like trick the car.
Wow, you'll just waste money. The worst risk is, like, you can do that, and you might even get like a small performance benefit. But the real danger is putting low octane fuel in like a high big performance engine, because then the explosion, the piston will actually outrun the explosion, and it's really bad.
Yeah, yeah. If it's not knocking, then it's kind of wasting money, because it's if it is knocking, then you better do it. Depends on how much carbon deposits you have too, because that'll change what they call the compression ratio and stuff. So you don't want detonation. I destroyed one engine by detonation.
Is that a Subaru blew up?
What's that?
Was that a Subaru blew up?
It was a Subaru blew up. My Subaru blew up because
They blew up.
I had just bought the Subaru, and I didn't know this. I asked them, the person I bought it from, is it for pump gas, or is it for, like, they have racing gas, which is 100 octane? And no, it's pump gas. So I put pump gas in there, 91 octane, and I blew up the engine. Yeah, it was tuned for 100 octane gas, which I could have gotten 100 octane. They sell it on Lomita and Western at VP. There's a pump with 100 octane gas there. But it's like $10 a gallon, so or more. So you don't really, if you don't need it, don't buy it. It's not gonna do anything.
In rally races, it's really preferred octane. A lot of like the road is like.
A lot of people have, but nowadays people are doing the inexpensive route. The inexpensive route is they use E85. That is 85% ethanol. 85% ethanol gives a lot of power to the car. But when you look at the fuel rating here,
You also wouldn't want to use it in a computer.
like if you look at methanol is 22.7 kilojoules of energy per gram. You know, and octane's like isooctane's like gasoline. So gasoline's around here. You know, and so this means you get a lot of power, but you have to use a lot of fuel for that. And so you need a bigger gas tank, and you need a bigger fuel pump and this kind of stuff. But it's cheaper. It's a lot cheaper than buying race gas. So most people who want power in their car, they have cars that are designed to run. It's called flex fuel. Have you seen flex fuel vehicles? Flex fuel. They have a detector that's in line with the fuel system that can measure how much alcohol is in the fuel, and then adjust everything accordingly, using just the computer. And so it can put in more fuel, and then it can do different things.
You can also retune your engine.
Yeah.
Run different gas.
So E85 it would be good. But anyway, getting back to this here. So the hydrogen, we'll see if the infrastructure gets there, but how long is it going to take? Because I don't know how long ago it was that they were promising, the governor was promising to build a whole bunch of hydrogen stations, but zero got built, I think, and so we'll see how long it takes to get the infrastructure in there.
It's like the train to Vegas.
Oh, no, those were the trains to San Francisco.
Yeah, train to San Francisco, that's in Sacramento. Train to Vegas, I think, would be very nice to have.
There's a bus to Vegas.
Yeah.
It's already $8
What if we put the bus on rails, and then we tied a bunch of buses together? So then we have both buses.
That's
off
a
the
great idea.
road.
Why don't we use
And
batteries?
John Sharp's presenting a train.
Anyway, this last section is Chem 1B. In Chem 1A, when we're looking at driving force is going from less stable to more stable. Stronger oxidizer to weaker oxidizer. Stronger reducer to weaker reducer. Stronger being less stable, weaker being more stable. Stronger acid to weaker acid. And so what we're doing is we're going down in energy. So it's downhill in energy. And so when we go downhill in energy, we expect it to be spontaneous. It's easy to go downhill. The going uphill is the difficult thing. But a weird thing happens. It depends on how steep and how far uphill we have to go. There are some uphill reactions that are spontaneous too. And you'd expect those uphill ones to be non-spontaneous because the driving force should be the reverse direction, not the forward direction. And it turns out, well, we have to look at two things. We have to look at the energies, like stronger oxidizer and weaker oxidizer, those what we call chemical potential energy. But we also have to look at one other thing, and the one other thing is not discussed until Chem 1B, and that is entropy. And so the spontaneous processes could be downhill like this, like rusting iron. That's spontaneous. This is downhill. This is minus 2,000 kilojoules downhill almost, or 1,600 kilojoules downhill. But you look at this uphill reaction here is spontaneous. We're taking the solids here. These solids are water soluble. There is a little bit of water generated here, so I don't know why they didn't put this as aqueous. Maybe it's just not enough water generated to dissolve that and dissolve this. But this uphill reaction is spontaneous too. So why is this going uphill? So this is going from weaker to stronger. And the key is number one, it's not going very far uphill. Do you see that? It's only 165 versus thousands. And so some reactions that don't go very far uphill can make it. And number two, a gas is formed. When we have gas forms, then it changes things because that introduces something that could sway the balance, and that's entropy. Entropy is this measure of order or disorder, and so when we form a gas, gases aren't very well ordered compared to liquids and solids. Solids are the most ordered, and liquids are a bit more ordered, but they're ordered in the sense that all the water molecules are touching, but when we get a gas, then it becomes totally disordered. It's hard to predict where the ammonia molecules are, whereas in a solid, it's easy to predict where the ammonium ions are. And so this entropy thing is going to be looked at in Chem 1B. And so there's going to be a lot more symbols introduced in Chem 1B and more equations and more restrictions. And so the most important thing that you can do for thermodynamics is get a good handle on these first. Q, W, potential energy, kinetic energy, delta U, delta H. If you can get a good handle on these QV, QP stuff, then you're going to be a better prep, because normally what happens is people will go through this and then they'll go into a class called thermodynamics. And then in thermodynamics, they don't have all the definitions sorted out in their head and they get mixed up. So they end up using the wrong equation for the wrong set of conditions. There are equations for different sets of conditions, and you have to make sure you're using the correct equation. And so when you go to thermodynamics part 2, you got to look, are you under standard thermodynamic conditions or non-standard thermodynamic conditions? Are you at 298 or not at 298? It all makes a difference in how you do the calculation. And so let's say if you're going into biology, then thermodynamics is very important for biology or biologists, because are you doing aerobic respiration or anaerobic respiration? And how much energy difference is there between aerobic respiration and anaerobic respiration? That kind of stuff. And for chemists, we do most of our stuff at 298 Kelvin, 25 degrees C. But in biology, if you look at biological thermodynamic tables, none of the data is at 298. You know what temperature they use? What's body temperature? 98.7. How about in degrees C? 37.5, 37.1, something like that. And so when you look at the thermodynamic tables in biochemistry books, they're all at body temperature. So all the numbers are a little bit different. You're used to looking at them at 25, but they're a little bit different at body temp. And so the problem is with thermodynamics, the situation is thermodynamics has an extremely high failure rate. And it has a high failure rate because it's easy to use the wrong equation for the wrong circumstance. And so, and then you have to just keep track. You have to keep track of everything. And so we start labeling, like in Chem 1B, we'll start labeling these with temperature. I don't know what temperature this is. And so I would just do delta, I do a delta HR. I don't like to write the R before the H. This is standard conditions, and then I'll write the temperature down here. Is that body temperature, or is that 298? You know, or is it some other temperature? Because we don't have to do reactions at either or. We can do them at any temperature. And so some reactions we want high temperature. And so if it's at 1,000 degrees C, I'd make a note of that. And so how does that impact all the other numbers? And so that's where things get confusing. And so the best thing to do here is to just get a handle on the definitions for all these symbols. We're going to see them again when we come back to it in chapter 13, I think. Well, again, if there are questions on calculations, you can ask me later. You'll see this again on the final. But for now, we're going to go back to atomic theory. We left atomic theory with Dalton's atomic theory. But, you know, Dalton's atomic theory, you can make some predictions. So, for example, you can predict the law of multiple proportions. But you can't really predict much else. Like if I'm looking at the difference between lead and gold, you know, Dalton's atomic theory just says the difference between lead and gold is they have different atoms. And the different atoms weigh different amounts. But does that tell you much about the properties of lead? It tells you nothing about the properties of lead and gold. And so we need more to it. And so those are our observations. You know, the periodic table over there was developed originally by who? Do you know? Mendeleev? There's another person who made the periodic table around the same time in the 1700s. So the periodic table's been around a long time. It wasn't as complete. But when you look, those are all observational data. Those are all observations of physical and chemical properties. And they group the elements according to their physical and chemical properties. And so in science, this is what we do. We take down our observations like that, and then we look for patterns. There's definitely a pattern there. Do you see the pattern? We got columns and rows. That's the pattern.
What year were you in high school or graduated?
Early 80s.
What did the periodic table look like then? Like, what did your periodic table look like?
My periodic table stopped at about here. These elements have been known for a long time, but the dispute was the names. And there was dispute about, you know, there's a big competition between Russian scientists and U.S. scientists about discovering these types of things. And so they had two sets of names, you know. They had a name from these scientists, group of scientists, and they had a name from another group. And then they wanted confirmation, you know. They just didn't want to believe that somebody said that they did that, and so they wanted, yeah. And so there's still some dispute. So this is a new name system, but this is an old periodic table too, and the names have changed for these. I think they've actually assigned names for them.
Imagine fighting over the name of a spec that exists for a picosecond.
Yeah, there's big fights about that. I mean, look at all this.
My spec.
America, you know, you don't even have to be, well, some of these, yeah, there's definitely some disputes because is it, you know, but I know one of these.
What's 116?
Well, then, did you hear about, what was it, element number 115, wasn't it, that one? There's some guy, who claims to have worked, at the, what's that place in Nevada called? No,
Area 51?
Area 51. Talking about the alien propulsion system using element 115. Did you hear about that? So I was looking at the properties of element
It's not
115.
stable.
But, oh no, it's not stable.
To us?
No, yeah.
What do you mean?
The aliens
It
stable.
blows us. It hates existing.
You gotta watch Ancient Aliens, man.
Yeah.
You gotta watch the Stargate.
Well, I know that I've met this guy before.
Wait, the guy who made the element?
The guy who discovered this element, Seaboard, Glenn T.
Oh,
Seaboard.
it's naturally occurring.
No, it's not naturally going. He
So
made
he made
it.
it.
He
Yeah.
made it. This guy was at he made a lot of these. This guy was at Lawrence Berkeley Laboratory.
Isn't there a Berkeley?
Yeah, there's Berkeleyum too.
Is it named from Berkeley?
Exactly. Berkeleyum. This is Californium.
Shut up.
American.
Is that what germanium? Germanium?
Germanium, yeah, germanium here. Germanium was one of the missing elements that was predicted to exist, and
When
then
did
they
you find
discovered it. What? Germanium.
Like decade wise.
What decade? That was in the 1800s.
Oh, so.
So, anyway, do you have a hypothesis? Well, it would be great because, you know, if this person was complaining the alien propulsion system ran out 115, then you would, if you had a hypothesis about, you know,
It's very demonstratable.
yeah, then we could see what about element 115 makes it excellent for propelling alien ships or whatever they use. So that's actually, I was looking into element 115 to see if there's something unusual about it.
Well, is it not true that if you had enough energy to somehow keep it stable, you might as well just use all that energy to propel yourself?
What's that?
To just, the energy required to just keep it existing?
Keep it existing. I don't know what the half-life. I was looking at the half-life, and the half-life is extremely short.
Yeah, it's like.
So to keep it existing, you don't keep it existing. It's going to decay. So you have to keep making it. Continually have to make it as it decays.
I'm not convinced of the
Yeah. So apparently this person has a lot of traction because he was interviewed by Congress.
Oh, that guy. I actually saw that guy on YouTube.
Yeah. Well, anyway, what we want is we want some kind. This is the law. You know, the law of the families and the law of the periods. In a family, you know, the properties just are very similar. They just change gradually. And the law of the periods is we start off with metals and it changes gradually to non-metals. That's it. So we have the law, and then we think of a hypothesis. Can you come up with a hypothesis for a more fundamental description of what's going on? If we had a more fundamental description of what's going on, then we'd know what's going on with element 115, you know? Why the aliens chose that? Why didn't they chose something more stable? You know, if they're going to use some kind of nuclear process to power their ship.
Oh, I have a hypothesis.
All right.
Well, it's a spaceship, right?
Well, I mean, not about this, because we want something, a theory that explains element 115 as well as all the other elements.
Well, yeah, but if you're building a rocket ship, it makes sense that you would want to go up.
Oh, yeah, you're right.
That's all the guys.
That makes total sense now. That could be, you know, how
Call
the,
Congress.
it could be how the YouTube guy discovered it was element 115, because it does make sense. It is, for sure.
I will publish a scientific paper.
Yeah, you could. But anyway, we look at this, and can you come up with a hypothesis? The underlying, why do we observe the periodic table? I mean, what's the explanation for the law of the period and the law of the family? Well, these are laws because, you know, otherwise we wouldn't be able to predict. You know, I mean, these are rules. There's exceptions to the rules. Maybe germanium's not there, it's over there. But
Oh no, once it continues a really good movie.
And so that's why we came up. And the thing is, this, I mean, what you start to do is you start to go back to physics. So going back to physics, we have the nucleus in the center of the atom, then we have an electron. An electron is a little particle and it's moving. And so we can model the movement of the electron using Newton's laws. And Newton's law says that the kinetic energy of the electron is equal to 1/2 mv squared, or 1/2 mu squared. You know, so we just need to know how fast it's moving, and then we can get the energy of the electron. And so you got these electrons around the nucleus, because the nuclear atom model was discovered well before back in the, when was the nuclear atom model? Around the 1800s, late 1800s, something like that. And so we go from helium, which has 2 electrons, to lithium, which has 3 electrons. And so why does lithium behave so differently than helium? And then when we go from lithium to neon, neon has 10 electrons. We're back to something that behaves like helium. And so that is not easy. And nobody came up with a good hypothesis for this. Do you know how the theory underlying chemistry came about? Well, that's what we're going to talk about here. They weren't looking at the periodic table and going, we need to get a good theory. That way we can understand this and we can make predictions. Which elements would be best for, alien spacecraft propulsion, that kind of thing, if we had a good theory. But it didn't come out that way. What happened was it was kind of came about in a roundabout way. And so since it came about in a roundabout way, that is serendipitously, we're going to look at the history of the development of the theory. And the theory that describes the periodic table is called quantum mechanics, or quantum theory. And so that's the modern day theory that we use to understand such things. So if I'm trying to figure out why the aliens chose element number 115, then I try to use quantum theory to try to understand what makes element 115 special. Something like that. And so it wasn't somebody looking at the periodic table and going, I'm going to hypothesize quantum theory. It wasn't that at all. And so this is going to seem kind of a roundabout way to get at it. And the roundabout way is initially through light. And so we'll talk about light and its interaction with matter first. And then we're going to use this quantum, once we look at the development of quantum theory, then we're going to use quantum theory to understand how the electrons are described in atoms, electrons in atoms. What is this? You know what that is?
A neuron.
Neuron, okay, yeah. Actually, there's a physicist at UCLA who was doing just straight physics, no biological applications, and then switched to biophysics. And this physicist developed this kind of hearing device that can listen to neurons. And when the neuron fires, there's a little electric discharge. And each time a neuron fires, if you listen to his listening device, you can hear a click. And it's so weird because I went to his talk. This is at UCLA, and he played a recording.
Sorry, is this implanted? Is this implanted?
No. It was I think they have some kind of cap that they use, but they had a mouse, and I don't think they implanted anything in his brain. They might have. I can't remember exactly, but they had.
Is it targeting a specific neuron or like a large group of
No, the whole brain.
Oh, well,
Yeah, and you could listen to the whole mouse brain, its neurons firing, real time. It's really bizarre.
Oh, is this how you find out that neurons shoot in like shots, not like continuously?
I'm sorry, what was it?
Is this how you find out how neurons shoot like by shots and not like continuously? Like it's a bunch of like.
Yeah, they're looking at
Oh, is this like it was found out, or it was like found out before and then you like visualize it now?
Probably the second, because why would you build it if you didn't know that?
No, they knew there were signals. They just want to hear. They wanted to hear how. And it's like, okay, you can monitor one neuron, but they wanted to monitor everything, the whole brain activity. And so it's pretty wild. So the development of quantum mechanics started with observations of how light we call electromagnetic radiation, and matter interact. And so this is not lightweight, this is just a string. And they're making a wave here using the string, and the wave is propagating. And so there's certain things that we see here. This wave, as it propagates here, what we will observe is there's going to be oscillations in amplitude. And so as this is moving towards me, I'm going to see it rise up and then dip down, and then rise up again and dip down. And so it's an oscillating wave. And what they're showing here is lambda. Lambda is the wavelength. So one oscillation is called a cycle. And so this slide is just saying that electric and magnetic fields propagate its waves through empty space or through a medium. A wave transmits energy. So what we're going to do is we're going to look at electric field. If we have an electric field, you know what an electric field is? An electric field is if you take a positive and a negative, like say a positive metal plate and a negative metal plate, you've just made an electric field. But this is called a static electric field. So one end is positive, the other end's negative. You can do this by pumping electrons or electricity in there. And you can have objects, matter, interact with a static electric field. So for example, if an object fell into there, and it didn't have any charge, it would just continue dropping due to gravity. But if there's a charge, then it'll interact with one plate or the other, one side of the field or the other. So if you drop a negative object in there, it's going to be attracted to the positive side of the field. If you drop a positive object, it'll be attracted to the negative side of the field. But when we have a light, what we have is we have an oscillating electric field. An oscillating electric field is going to be like this. In one instant, it's positive here, but as it's moving to you, then it's going to oscillate down to negative. And so what's going to be happening is the field is going to be switching between positive and negative, like this. And so in one instant, it's like this, positive on the top, and then it flips to positive on the bottom, and then just keeps flipping back and forth. This is called an oscillation here. So let's say you're a negative particle. If you're a negative particle, you're going to be attracted to the positive. You're going to follow the positive oscillation. So if it's positive up here, you're a negative particle, you move up. And then as it goes positive down here, you're a negative particle, you move down. And so what's going to happen is you're going to be moving with the field as well. So the field's moving like this because it's propagating, it's coming to you. And then the way your matter and the way you're going to interact with the field is if you have a charge, you're going to interact with one end or the other, and pretty soon you're going to be oscillating. And when you oscillate with the field, we call that resonance. So you're resonating with the field. Does that make sense?
How does the field know which way is down?
How does the field know? There's no down, there's no up. It's just either positive or negative when it hits you. It's like this. If you're a little, this would be on an ocean wave. Let's say if this were an ocean wave and you're on a little boat, you would be oscillating with the waves, up and down. Ocean waves. This is amplitude here. And so light consists of an electric field component, which is this plane here. And so that's this red line. And do you know how fast light moves?
About 300,000 meters a second.
Yeah, it moves incredibly fast.
Is it 300 million or 300,000?
300 million.
Oops, yeah,
300 million meters per second. And so it's moving at the speed of light. And so these oscillations can happen very, very fast. Not only do you have an oscillating electric field, you also have an oscillating magnetic field. The magnetic field we think of as being perpendicular to the electric field. So if you're a little magnet, what's happening is it's switching. And so if the field is going north pole here, then you're south pole up here. Then all of a sudden it goes north pole down here, and then you have to flip And so if you're a little magnet, you would be flipping back and forth. In other words, you would be resonating with the magnetic field oscillations too. Primarily, we're just going to look at the electric field oscillations. You know, a lot of people are concerned about electromagnetic radiation because they worry about, you know, what the electromagnetic radiation is doing to your body. And a lot of people are saying that magnetic field is worse than electric field. And so people buy these. Some of my friends have these, and they go around to the microwave, TV, the electric outlets, and they're looking for, you know, the strength of the electromagnetic radiation coming off there. And then you can buy shields. Like I got a gift from my sister. My sister bought me an electromagnetic shield for my phone. I haven't put it on there yet because it's a little too bulky, but it's supposed to protect me from the oscillating electric and magnetic fields. What's that?
Well, if it actually works, then it would block shortwave radio, which means that your like tap to pay wouldn't work. So if you put the phone case on and that work, and that doesn't work, then congrats, you're doing something unnecessary. But if it does work, the phone case is full of.
Yeah, that's true. I could check it with that. Sure. Well, but anyway, we have these oscillating electric and magnetic fields, and so we can do different things. We can look at the amplitude. The amplitude is how big these peaks are. Or we could look at the wavelength. If we look at the two wavelengths here, this wavelength is longer than this one. So this is what we call shorter wavelength light. This is longer wavelength light. With shorter wavelength light, the oscillations are going to be happening much faster because both of these are moving at the same speed, the speed of light, which is like 300 million meters per second. And so this one's going to be oscillating faster, this one's going to be oscillating slower.
Come to think of it, if you truly had a phone case that blocked EMF, you wouldn't be able to make a phone call.
Yeah.
Why would that sound like the worst phone case ever?
Yeah. Well, yeah. Maybe it you know, there's got to be a transmitting antenna or something. Maybe they don't block that. I don't know. Maybe it's facing this way. I'm not sure how it works. But you could try to shield. I mean, we could try to shield ourselves from this. I went to a room which was shielded for electromagnetic radiation. And, they just had a lot of mesh on the walls, metal mesh, and the room. This is for testing audio components for noise. And so they didn't want any interference there. So it completely blocked off all radio waves and everything else from entering the room.
This is cool. I have really sensitive, like low resistance headphones, earphones. And I put them into a radio. I switched the radio off, took the battery out, and it would still, I would still hear something.
Oh wow, that's pretty cool.
It was the ghost.
Well, speaking of radio waves, let's take a look at radio waves first. So this is called the electromagnetic spectrum, which is going to go from radio through microwaves, infrared, visible, ultraviolet, X-rays, gamma rays. And all these are going to be either characterized by frequency, like radio waves are typically characterized by frequency. And frequency is, let me talk about that here. Should I show? Frequency is going to be expressed in units of hertz, Hz. And a hertz is a cycle per second. And so if we start up here and drop down and then end up at the same place, that's called one cycle. So one full, what we call wavelength, passes by. A wavelength is peak to peak or valley to valley distance. And we're going to have a lot of those cycles per second because light is moving so fast.
When can we expect a exam for that? Or like when to discuss?
It's going to take a little bit of time to get the exam. So next week, end of next week probably.
Oh, okay.
Yeah.
Sorry, when is?
I still have some people who haven't.
In EMF, I haven't actually.
I'm sorry?
When is hertz used when talking about light? I haven't heard that.
You haven't heard hertz?
it's usually wavelength.
It's usually wavelength for radio waves. The radio waves, for example, if you look at the length of the wavelength of radio waves, take a look at the length here.
Well, not just radio waves. Like I know that green on the top of my head is 440 nanometers. Like it's just a very convenient.
Yeah, yeah. Like 10 to the third meters. 10 to the third meters, 1,000 meters is a kilometer. So this is 1 kilometer. So the peak to peak distance in a radio wave is 1 kilometer. But radio, you know, when you tune your radio, I don't know if anybody listens to radio anymore, but like they'll say, okay, this is 99.9 megahertz. Have you ever heard that? Or it's like 92.8 megahertz, whatever radio station, you know. AM is in kilohertz, FM is in megahertz. And so FM radio is in megahertz. Megahertz is 1 million hertz. A hertz is 1 cycle per second. And so the frequency is given in seconds to the -1, which is a cycle per second, though people don't write cycles. And then this is called a hertz, an Hz is a hertz. And so FM and AM radio are typically in hertz. AM radio is in kilohertz, so it would be like, 900 kilohertz on the dial, And so AM is here. And so when we think about like this, it used to be in the old days, because I went to when I was in high school, everybody had metal car antennas that stuck out like 3 feet, and then sometimes vandals would come along and break off the antenna. You ever seen that? And then what you'd see in the high school parking lot are cars with a metal coat hanger jammed in where the antenna is supposed to be, so that they didn't lose their reception.
Wait, that works?
Yeah, it worked. It worked. And some people they'd have this little triangle thing that looked like an alien vehicle, but it's just some coat hanger. So it's kind of funny.
Coaxial cable to be an effective antenna.
You'd need coax when you get to higher frequencies. So when you get to microwaves, you would need coax, and you'd need waveguides and this kind of stuff, but not.
That's crazy.
Yeah, and so why metal? I mean, you could try a plastic coat hanger. Would a plastic coat hanger work? Or wood coat hanger? Let's say somebody found a branch and they jammed a branch into where the antenna is supposed to be. Do you think a branch of wood off a tree would work? It would be great if it worked, because then, if somebody broke your antenna off, then you can just get radio reception right away. Sometimes it's easy. Sometimes it was easy to break off. I've accidentally broken off an antenna because you lift it up and then sometimes something gets knocked onto it or something and breaks. But it used to be very easy. Nowadays it's hard. The antennas are a lot smaller, much more compact. But what would happen is this. A radio wave would come along, that's megahertz, 1 million cycles per second. And then it's oscillating like this. So it hits the antenna, and what does it do? Well, it's an oscillating field, so it's plus, minus. And it's got to be metal, because metals have loosely held electrons. And electrons are what charge? They're negatively charged. So if you have an oscillating electric field and you're negatively charged, you're going to be attracted to the positive, not the negative. You're going to be repelled by the negative. And so what's going to happen is the electrons are going to start oscillating or resonating with the field. And so that's what happens. Whereas in plastic or wood, the electrons are so tightly held that they can't oscillate easily. Right? And so the radio waves hit the antenna, they excite the electrons. And so what we say is that radio waves and matter, radio waves excite electrons in matter. But not all matter. It has to be matter that has loosely held electrons. Well, what matter has loosely held electrons? Pretty much just metals. You could use something like graphite. You know, graphite also conducts electricity, but graphite wouldn't be as good because it only conducts electricity in a plane, not in 3 dimensions. And so plastic wouldn't work. The electrons are too tightly held. Wood wouldn't work. The electrons are too tightly held. Right? But maybe in neurons, maybe the electrons aren't. I don't know. Would it work in neurons?
I feel like some days my neurons are pretty tightly held, and other days they're loosey.
Yeah. All right, and then we transition. You know, pretty soon, radio waves is a pretty wide part of the spectrum, but then we go to microwaves. Microwaves are oscillating faster. For microwaves, we still use hertz. Like a microwave oven. A microwave oven, as I recall, is a 4.5 gigahertz. Cell phones are gigahertz. So cell phones are kind of in this radio microwave region here, in the gigahertz region. But what microwaves do, they can excite electrons, but it's a bit more difficult. Have you ever put a metal inside a microwave?
Yeah.
If you have, you see lots of sparks. And you see lots of sparks because electrons get too excited. You know, microwaves are, you know, radio waves are just right. And so you can use this to get the music off the signal. Radio waves will have the information contained. But you throw metal into a microwave, it's too much for metals. Electrons get too excited, and they're trying to resonate, and pretty soon they just break free. As electrons break free, we call that ionization. And so don't put metals into microwaves. Or don't put lead ceramics or lead glass in a microwave either. Because lead, you know, when you look at lead has a lot of electrons. Lead has 82 electrons. And so if you put lead into a microwave, that's bad because lead has so many electrons. It could be, you know, it doesn't have to be lead metal, but it could be like lead crystal or lead ceramics. You know, I put a dish into the microwave and it was so hot, I got a second-degree burn when I grabbed it. You know, and then I thought, well, there's got to be some lead oxide. It was white ceramic, so I was thinking, the only thing I was thinking is probably lead oxide in that ceramic.
Oh, I have lead oxide in my ceramics.
Yeah, lead oxide's used as a white pigment for a lot of things. Like, I think a lot of the artists still use it. But I did stop putting that in the microwave.
Wait, should I stop eating off of those?
No.
No, keeping low.
But primarily, what do you use your microwave ovens for, if you have one? Some people don't have them. Heat. And so what microwaves do is this. Microwaves are known to rotate small molecules. So if you have a water molecule, one end of the water molecule, the oxygen end, is negative. The hydrogen end of water is positive. So if you have an oscillating field like this, the water molecule is going to want to flip. Because, you know, let's say the oxygen likes positive, so it's up here, and then all of a sudden it's down here, and the oxygen is going to try to follow it. And so the water molecule is going to flip and then start to rotate. And we call that rotational kinetic energy. And if you got kinetic energy, then we call that heat, and the temperature is going to go up. And so microwaves are tuned to flip water molecules, to rotate them, and then we get the kinetic energy, and then we get the heat. We also have microwave spectroscopy. Microwave spectroscopists look for small molecules out in space or wherever, or on Earth, you know. And so they're looking for alien life, you know. They're looking for evidence of water or CO2, not CO2, but other polar molecules out there. Infrared is going to be oscillating faster. Infrared, we stop talking about hertz. Like radio, we typically look at hertz. Microwaves, we look at hertz. Infrared, we're going to start looking at meters. You know, how long the wavelength is. 10 to the minus 3 is how many meters? 10 to the minus 3 is, 10 to the minus 2 is a centimeter. 10 to the minus 3 is micrometer. And so typically when we talk about infrared, people talk, if you talk to infrared spectroscopists, they talk about microns. Microns is a micrometer. And like how many microns does it absorb out? This kind of stuff. There's a special unit that chemists use called wave numbers, but that's a unit of energy. We'll talk about that later. But infrared, you know, what's easier, to rotate a water or to get it to vibrate? Actually, it's easier to rotate it than to get it to vibrate. And what infrared does is this causes vibrations in matter. So the hydrogen is positive, the oxygen is negative. And so as the field oscillates, so does the bond. And that causes the bond to oscillate with the field. And so this causes vibrations in water molecules. Or food. You know, a lot of people cook. They have these, like charcoal. You know, you got these red hot charcoals, and there's no flame there, but it's radiating lots of infrared. You can feel the infrared. You can't see the infrared, but if you put your hand over the charcoals, you can feel the infrared radiation coming off there. And it's causing the atoms in your hand to vibrate. And so you can feel the heat. And so infrared is used for cooking. Microwaves are used for cooking. That's because we're getting kinetic energy and we can increase the temperature that way.
Do electrons move between shells or no?
Yes, electrons can move between the shells, and that brings us to visible light. You know, infrared's invisible, and then we start to see visible light here. It's a very small part of the spectrum in terms of wavelength. But the first light that we can see coming off infrared is what's called what? What do you call this color? Red. Red light. And so sometimes you have red hot coals. If you have red hot coals, it's starting to emit some visible light, which you can see, but you can definitely feel the infrared. So there's infrared light being emitted here. You can feel that, but you can see the red. What visible light does is this. Visible light excites electrons. And so this would be exciting electron from one shell to the other. Or it could excite electrons within the same shell. So it could go from what we say one orbital in a shell into another. And so these are called electron excitations. It's enough to excite the electrons but not ionize them. And so we excite the electrons here, and it depends. And so we're going up in energy. Slightly higher in energy than red light is, what color would you call that? This color here. This is orange. And then, do you see red spans a kind of a wide spectrum? From 760 to maybe about here. And then orange would be about from here to about here, and then the orange transitions to a what color? What do you call this color here? I'd call that yellow. Color is very tricky because some people will say, no, this is not really orange, that's red. Maybe this is orange, yellow, something like that. Red, orange. And so it's quite tricky. I mean, there's some people who look at, like, where was I? I was in Japan, and they're saying, oh, the signal's turning blue. I'm thinking, blue? It looks kind of green, you know, to me, but color is kind of subjective. And so rather than saying, you know, oh, the signal's turning blue, I just say, oh, the signal's turning to 475 nanometers of wavelength there. And then that would be clear. No dispute there.
Oh, you think? I have a friend who's an artist, and like they have to deal with like the reality of color instead of like the ideal of color. So the arguments about like how a color works are like it's just insane.
Yeah, it's pretty.
You can't mix up paint to reflect 475 nanometers. That'd be extremely difficult.
Yeah, it would be extremely difficult. It'd be cool if you could. I mean,
That would look insane.
yeah. But anyway, there's a range. So there's a range of colors for orange, a range of colors for red, yellow. What's next here? What do you call that? Yeah, some people call this blue. I call it green. What do you call this one here? Blue. What would you call this color out on the end here? Purple, but we'll call it violet. And then, between blue and violet, we call that a color, even though you might think, why bother? We call that indigo. I can't really, if somebody showed me an object and said this is indigo, I can't really tell, it's hard for me to tell what indigo is. But it's there. And one way you can remember this is the mnemonic Roy, actually this is wrong. What is it? It's Roy G. Biv. And so this is going from low energy visible light to higher energy. And so, some people, they're worried about blue, indigo, violet light because they're worried about eye damage. It's exciting their optic nerves too much. You don't want to excite them too much because there could be damage associated with that. Even infrared, you think infrared's not that bad, but I used to work in a laboratory where we used infrared lasers. I hated it because the thing is this. If you get hit with infrared laser light, you're blind. You're going to be permanently blind.
Well, if it's like a lot.
It's a lot. It's always a lot. When that laser's pumping.
No, I said a watt.
Oh, watts?
Was it like a pulse laser or was it a...
Yeah, it's a pulse laser. When you look at it, you're going, wow, that. Yeah, I don't even want to touch that because it'll probably burn a hole through my hand or something like that. But yeah, it's scary. And then you're adjusting the mirrors, and say you screw up adjusting one mirror and it shoots off here and then hits you in the eye, and then you're blind, and it's like. There's all these warnings, and you have to do these safety sign-offs and all this stuff because they don't want to be responsible if you accidentally blind yourself.
You ever hear of, I think his name was Antonio Bugorsky? Have you heard of
Oh,
his name?
yeah, the guy who got, yeah.
He put his head in a particle.
Yeah. Unfortunately, he didn't survive. It would have been great if
Well,
he
he survived
survived.
a while. He
A
survived.
while.
He didn't die
But
on
you
the
just
spot.
think about how much pain it must have been. I mean, that's horrendous. Yeah, that's the exact same reason why I was thinking every time I go into that lab, it's like I'm risking my vision, Because what if my goggles were up here and I didn't notice it? My goggles were up here and I was playing around with the mirrors and boom, get hit in the eye. Or, or something else happens, It's incredibly risky. But, so even the infrared can be dangerous, but people are worried about blue. Indigo, violet, because they're saying that, and there's been studies that have shown that these can cause damage to your eyes. And so they have blue blockers. Have you heard of those? Blue blockers, and now computer monitors, they have things to reduce the amount of blue coming out of those.
Blows my mind. My mom got a pair of blue light blocking glasses for that reason.
Okay.
And they're just completely clear. And I'm like, oh, you were scammed. Like, they're full of shit. It doesn't actually block blue light. Because they're not. Because if it did, it would be slightly yellow. And she just can't comprehend the fact that it's not. She's like, no, it's blocking blue light. And I'm like, yeah, that would make things yellow, but it just doesn't penetrate.
It depends on how much blue you want to eliminate. You don't have to eliminate 100% of the blue. You just got to reduce the peak intensity, that is the amplitude of the blue down. And that'll help, because the less intensity. And so that brings us to the...
If there's no visible difference, then it doesn't mean anything, right? 'Cause there's
Well,
no visible difference.
you have to put it in a spectrometer and see. If you put it in a spectrometer, you can easily detect how much it reduces the intensity of the blue light. And so it might be doing something.
Even if you look at the color wheel and it looks exactly the same without the glasses on, you can still be doing something.
It depends on.
Yeah, look at color wheel.
It depends. Well, the color wheel is important, so we'll look it up. So if you want to block blue, then it should look what.
Should look darker.
Yeah, it should have an orange tint to the.
Yeah,
It should. If you could completely eliminate all blue, but what we're trying to do is not just block blue, but we're also trying to block indigo and violet. And so you're right, it should have more of a yellow tint to that, orange yellow tint.
Almost a lot of the blue light blocking glasses I've seen do. So I'm like, oh, so you're lying.
Yeah, but yeah, if it's blocking it, but it's hard to find a filter that blocks 100%. So usually you have different filters, levels of filters that'll just knock off the top, and that. Knocking off the top could be a big saver, but even if a little bit of blue leaks in, it's still going to look fairly colorless. But I mean, it's something that's not too difficult to test. I mean, you could test it here, actually. We have the equipment. Anyway, we're out of time, so we'll talk about this next time.
Professor, do you think it's worthwhile to memorize like the wavelengths?
No, we don't memorize. We memorize this.
Are you buying lasers on eBay?
390, 760. Memorize that, or memorize 400 to 800. The reason it's very useful to know that, because let's say you're being exposed to 300 nanometer radiation, then you'd know that's UV. You want to get out of there.
Will it be on the exam?
Yeah, certain things will be like.
What's the exam looking like so far? The ones you've graded, how is it looking?
What's our average on this line?
I don't know what the average on the Scantron is, but the Scantron was pretty wide range, so I'll see. But I took a look at some of the free response answers, but it's hard to say right now. I looked at some of the reactions. I'll talk more about it later. There's still a couple of people that need to take it.